Hello and welcome. This is going to be our lecture video for the Unit 5 review on rotational dynamics. Let's go ahead and get started with problem number 1. Here we need to convert 4 revolutions into degrees. So we'll start with what we know, which is that we're dealing with 4 revolutions. And I'm going to multiply by something that's going to turn revolutions into degrees. See, now I put revolutions on the bottom, so revolutions will cancel. Now I just need a true comparison between revolutions and degrees, and I know that in 1 revolution, there are 360 degrees. Now revolutions cancel out, and I just multiply across the top, and I get that 4 revolutions is 1080 degrees. Let's try that same thing with problem number 2, 4 revolutions into radians. Again, I start with 4 revolutions. Now, this time I need to multiply something that's going to turn revolutions into radians. And I know that 1 revolution is 2 pi radians. So revolutions cancel out, and this time I get 8 pi radians. But you're also welcome to convert that to a decimal if you would like. 8 times pi is 25.1 approximately radians. All right, let's try going a different direction, like from degrees to radians. So if I start with 540 degrees, I need to multiply that by something that will turn degrees into radians. So I know that in 2 pi radians, there's 360 degrees. Or I could use that in pi radians, there's 180 degrees. Either fact works, we're going to get the same answer. So now I multiply across the top, so 540 times 2 pi. I press enter, and then I divide by 360, and I get 9.42. And that is radians, because degrees canceled out. All right, let's move on to the next section. Find the length of each arc. So the formula here is just arc length equals r theta, radius times angle. But really important here is that that angle has to be given in radians. And then our answer will be in whatever unit our radius is in. So in problem number 1 here, we can't just directly multiply the 315 times the 11. We have to first convert the 315 degrees to radians. But this time I'll multiply by 180 degrees is pi radians. To get that 350 degrees, is equivalent to 5.5 radians. So that 315 is 5.5 rad. And now I can just multiply radius times radians. So S equals r theta. S equals our radius, 11 feet, times the radians, 5.5. 5.5 times 11 is 60.5. So S equals 60.5. Our radius was in feet, so this is still in feet. All right, let's try one where it's already given in radians. This makes our life easier, like in problem number 4. S equals r theta. The radius is 13 inches. The angle in radians is pi over 6. And now I can just multiply this out and turn it into a decimal. 13 times pi divided by 6 gives me 6.8. And the unit there is inches. As notice, the unit on our radius is inches. All right, on to section 2, angular velocity. We need to do some more conversions. First up, 32 RPM into rads per second. So when I write out that 32 RPM, I'm going to write it as 32 revs per minute, like a big fraction instead of RPM, revs per minute, revs on top of minutes. Now I need to get this into rads per second, so I need to first convert revs to rads. So I need to use one of that conversion ratio that turns revs into rads. I know that 1 revolution is 2 pi rad. Okay, 2 pi. Now revs will cancel out. My new unit on top will be rads. Now I just got to get seconds onto the bottom. So I need something that will turn minutes into seconds, with minutes on top to cancel this minutes. And I know that in 1 minute there's 60 seconds. And as I multiply across the top and then divide by the bottom, which is just 60, I get 3.35. And then our unit there is rads per second. All right, let's set up this next one. 450 degrees per hour, so 450 degrees per hour into RPM. So for that one, I would want to do 1 hour is 60 minutes. And multiply that by the fact that in 1 revolution, we have 360 degrees. Now degrees will cancel out, hours cancel out, and the units I'm left with are revolutions per minute or RPM. And rads per second is going to be a slightly different setup, but I'll let you try that one on your own. Let's move on to maybe number 3. Washing machine is spinning around a sock with a radius of 0.3 meters at a speed of 25 RPM. Find the linear velocity of the sock in meters per second. So the formula here for linear velocity is V equals WR. The only trick is that angular velocity has to be given in rads per second and not revolutions per minute. So we have to do this conversion again, 25 revs per minute times 1 rev equals 2 pi rad times 1 minute equals 60 seconds. And we get that 25 RPM is the same as 2.6, and that is rads per second. So that would go in for our angular velocity W, and the radius will be 0.3. If I multiply these two together, I get 0.78 in the unit for velocity is meters per second. All right, next one. Yo-yo is being spun around on a string that is 0.5 meters long, such that the linear speed is 14 meters per second. How quickly is it being spun in both RPM and rads per second? So we got to use this formula backwards. V equals WR. This time we've got the V, we've got 14 equals our angular velocity times our radius, which we're also told is 0.5. Multiply both sides by 2, and we get that W equals 28 rads per second. So that's our rads per second answer. Now let's convert this to revolutions per minute by multiplying by 1 rev equals 2 pi radians, and 60 seconds equals 1 minute. And multiply 28 times 60 on the top, and then I'm going to divide that by, in parentheses, 2 pi. You got to put the 2 pi in parentheses. Try this one. Make sure that you get 267 RPM. All right, and moving on. Ant is sitting on the end of an hour hand of a clock that is 10 centimeters long. How quickly is the ant moving in meters per second? So again, we're going to do velocity equals W times R. We got to figure out the angular velocity. So we know that the hour hand revolves every 12 hours. So it's 1 rev per 12 hours. Well, let's multiply this by 1 rev is equal to 2 pi radians. We multiply that by the fact that in 1 hour we have 60 minutes, and in 1 minute we have 60 seconds. So revs cancel out, hours cancel out, minutes cancel out, and our final units are rads per second, exactly what we wanted. 2 pi on top, divided by, in parentheses, 60 times 60. And I get an omega, or lowercase omega, W, of 0.00174. Makes sense that it's very small. Our hands turn very slowly. Now I'm going to get my velocity, I need to do W times R. So I'll use this as my W, but for R, I need to use 0.1 meters, because we're given a length in centimeters. So I'll take that number, it's still my calculator, multiply by 0.1, and I get a very small number, 0.000174 meters per second. All right. Number 6 is another just V equals WR. Number 7 is a little bit different. We're sitting on a merry-go-round, 2.5 meters from the center, and it makes 24.5 revolutions. So how far do I travel? Distance, not displacement, and we got to use the arc length formula. So S equals R theta. The only thing I need to do is convert my angle into radians. So it might not look like an angle, but 24.5 revolutions is an angle. Let's just multiply this by the fact that 1 revolution is equal to 2 pi radians. And we get that we're traveling 153.9 rad. That's what I'll plug in for theta. And then for my radius, I'll put in 2.5. So times 2.5, and I get 384.8 meters. Even though I haven't really gone anywhere, by spinning around that merry-go-round, I've traveled 384.8 meters. All right, and on to a few questions about pendulums. So if a pendulum swings 25 times in 60 seconds, what is the period? We'll just use this formula up top, that the period is equal to time in seconds divided by number of swings. So 60 seconds divided by 25 swings, and what you'll realize here is we're finding the length of just one swing. So 60 divided by 25 equals 2.4. So it's 2.4 seconds per swing. All right, what is the length of the pendulum in the problem above? So now we're going to use the other formula, and we're going to plug in 2.4 for the period. So we get, I'll write it over here, 2.4 equals 2 pi times the square root of our length, which is unknown, divided by 9.8. I'll divide both sides by 2 pi. 24 divided by 2 pi in parentheses, very important, is 3.82. All right, to get rid of the square root, we got to square both sides. And we get 14.6 equals L divided by 9.8, and then we got to multiply both sides by 9.8. You get 143 meters. So to swing that slowly with an arc of 2.4 seconds, it looks like we would need a pendulum that's 143 meters long. All right, the next question is just a conceptual one. If the pendulum is lengthened, does the period get longer, shorter, or stay the same? It gets longer based off of this formula up here, which includes length. It's on the top of the fraction, so it's going to make the period longer. Let's just write out longer. And number 4, if the mass of the pendulum is doubled, does it get longer, shorter, or stay the same? This one's going to be a stay the same. Mass is not part of the formula for the period, so it stays the same. All right, torque. Simple formula for torque. Torque equals force times radius. So for all 3 of these problems, all you have to do is just multiply the force and the radius. This one here is going to be 60 Newton meters. This one here is going to be 300 Newton meters. And this one here is going to be 10 Newton meters. All right, what must be at M? So it balances. We've got 1 kilogram balancing 50 centimeters away. So this kilogram over here is going to be exhibiting, well, we don't have to turn the kilograms into newtons if we don't want, because we would just be multiplying by 9.8, and then we'd have to do it to the other side. So it's really 0.5 kilogram meters being offered by this weight right here. Now this weight over here is 12.5 centimeters from the end, so it must be 37.5 centimeters from the middle. And we know that our torques must be balanced, so the torque on this side, which we're seeing is 0.5, needs to equal the mass times 0.375. For the radius of the second mass, I'll just divide both sides by 0.375, and I get 0.5 divided by 0.375. I get a mass of 1.33 kilograms. And does that make sense? I think so, because it's a little bit closer in, so it should be a little bit heavier. All right, another one where the torques need to balance. So this mass is, we can even just say it's 3 units away from the center. This one's 4 units away from the center. So to keep their products balanced, this one has to be 30 newtons right here. And on to some rotational momentum and moments of inertia problems. We'll start with number 1. Momentum of a truck. So this is just linear momentum. So we'll use the formula P equals M times V, which equals 3,500 times our velocity of 52. And we get 182,000, and that is kilogram meters per second is our unit of inertia, or of momentum. All right, number 2, angular momentum of a 5 kilogram mass traveling at a velocity of 3 meters per second or on an arc of radius 4 meters. So let's start taking this apart. First, I need to find the angular velocity. So I'm going to use the formula V equals angular velocity times radius. I know that the velocity is 3 meters per second. I don't know the angular velocity, but I know the radius is 4. So divide both sides by 4, and now I know that my angular velocity is 3/4. And that's going to be rads per second. So now that I know the angular velocity, I can almost get the angular momentum. I do need to find the inertia as well. So inertia is equal to mass times velocity squared. So our mass is 5 kilograms. Our velocity is 3 squared. So 3 squared is 9. 5 times 9 is 45. For our inertia, and now I can figure out the angular momentum by doing L equals W times I. So 3/4 times 45 equals 3/4 times 45 is 33.75. And I'm not going to worry about the units of angular momentum. Just leave it as 33.75. All right, centripetal force, we got a different equation for that. Centripetal force is equal to mass times velocity squared divided by the radius. Let's start making sure we have all these values. We've got mass, we've got radius, but for velocity, where you've got an angular velocity, we need to convert that. So let's first start by converting our 5 revs per minute into rads per second. So we know 1 rev is 2 pi rad, and 1 minute is 60 seconds. And so now 5 times 2 pi divided by 60. I know that my straight line velocity is going to be 0.52 meters per second. I think I've got everything else in this problem. So 0.2 for the mass, 0.52 squared for the velocity, and the radius is 0.45. Let's plug all this into our calculator. And I get a centripetal force of 0.12. And because I did everything in SI units, the unit for this is newtons. All right, and on to our last question. Explain why an ice skater spins faster when they bring their arms in during a spin. The real key here is the conservation of angular momentum. All right, so we need all the same momentum. So if we decrease the radius, the velocity has to increase in compensation. All right, we'll call that good for this lecture video. Have a good rest of your day.